So friends, welcome back, and as per my promise and going ahead with the last lecture, today we are going to talk to you about the application of an AC voltage to an inductor, which we know that is defined by E is equal to minus L di dt. Okay. So this is a very simple circuit in which we have an ideal source of EMF alternating and an ideal inductor. An ideal inductor, though it is wound of metal coils, but it does not carry any resistance, or the resistance carried by it is taken as equal to 0 to make our life safer. Okay, so now in this circuit we will apply KVL, Kirchhoff's voltage law, and then we write V minus L di dt is equal to 0, which says that V is equal to L di dt, no problem. So I can write di dt as equal to 1 upon L into V. Okay, and V I can write as Vm sin of omega t. And when we integrate it, naturally then as the next step, then I get integral di dt dt and Vm upon L integral sin omega t dt. Or I can write this left hand side as integral di, and the right hand side I complete the integration Vm upon L into 1 upon omega, because of this factor omega t minus pi by, I'm sorry, omega t over here. So, and I told you, if you remember, that integral sine of theta d theta, integral sine of theta d theta, as also integral cos of theta d theta is equal to sine of theta minus pi by 2, that is the phase enhances, okay, or cos of theta minus pi by 2. That means the phase upon integration increases by minus pi by 2 radians. Okay. So by applying that, and in differentiation, the phase increases by plus pi by 2 radians. So here I am giving an increase of minus pi by 2 radian or a decrease of pi by 2 radians, and I write it like this: Vm upon L 1 upon omega sine of omega t minus pi by 2, and this sine of omega t minus pi by 2 is equal to minus cos of omega t. So when we carry out the integration, we get Vm upon omega L into minus cos of omega t. Okay, where minus cos of omega t is equal to sine of omega t minus pi by 2. And it is found that this constant of integration turns out to be equal to 0. Okay. So I can write this equation as I is equal to Im sine of omega t minus pi by 2, where this Im is equal to Vm upon omega L. So this is Vm upon XL, where X is a reactance, XL is equal to omega L, and it is of course in ohms, just like that. Okay. Actually, we can write this XL is equal to Vm upon Im, and then we translate into capital V upon capital I, the effective value is equal to omega L, and that is expressed in ohms. Just like our Ohm's law, that R is equal to V upon I. So here the XL is there, and this we call the inductive reactance in ohms. I have just drawn, as I do normally, that XL as a function of omega. This is a straight line, the slope is equal to L, etc. Now we compare the phases. Compare the phase of what? I, here the phase is omega t minus pi by 2, of course, and here the value of V is equal to Vm sin of omega t, the phase is omega t. Of course, we can compare the phases if this is also sine and this is also sine, this is also cosine and this is also cosine. Okay. So that way we find that this phase in the case of current is less than the phase in the case of voltage. Okay. So that means if we compare the phases, then we find that the phasor I lags behind phasor V by pi by 2 or 90 degrees. Or conversely we can say that the voltage leads the current by pi by 2, which I have shown here in a few diagrams. Okay, just like that, I take V like this, straight line, then I has to be in this direction. If I take it like this, okay, then I will be lagging behind by 90 degrees. If I take I like this, then V will be leading it by 90 degrees or pi by 2 radians. Okay. Next, we'll have the timing diagram and the magnitude of P, the instantaneous voltage. So we found through our discussion for this circuit, where we have ideal source and ideal inductor, that V is equal to Vm sin of omega t, which we can write as capital V under root 2 sin of omega t. Okay, and I is equal to Im sin of omega t minus pi by 2, which I can write as I root 2 sin of omega t minus pi by 2. I have tried to express it in the form of a time diagram. So first look at the voltage here. Okay, the voltage here, and this voltage goes like this, like a simple sinusoid sine of omega t. Okay, so then I have plotted this I is equal to Im sin of omega t minus pi by 2. Okay, with the red ink. Okay, you can see that by just looking at it, how can we say which one is leading the other one? Okay, which one is leading the other one? So let's see an event. For example, there is a point here, okay, another point over here on the two different curves. Point number one, one dash, or whatever you want to call it. You can see that here the function is at the peak and then going down. Positive peak. Okay. Now, which event is taking place earlier on the same time scale? So you can see that this is happening before this has happened. So that this one is the leader, the green one is the leader, and this is the one which lags behind. Okay, let's compare another case. This is zero crossing. Okay, zero crossing from positive to negative, and this one is also zero crossing from positive to negative. Okay, so can you say which event has happened first? This event on the left has happened next. Okay, similarly we can have this and this. We can compare. Okay. And every time we compare, we find that the green one, which is far voltage, leads the current by pi by 2 radians. I've shown it as pi by 2, 2 pi by 2, 3 pi by 2, 4 pi by 2, 5 pi by 2, 6 pi by 2. I don't subscribe to this 4 pi by 2 as 2 pi. No, or 2 pi by 2 as pi. I don't write that. I don't advise you to write like that, because the unit has been pi by 2. The same I can do in terms of time, and then the units become capital T by 4, 2 capital T by 4, 3 capital T by 4, etc. Okay, so from the time diagram itself, by the analysis that I've made, we can say that V leads I and I lags V by pi by 2 radians. Okay. Next, let us take, can't write even a proper spelling. Okay, instantaneous power P is equal to VI. There is no R in the system that I could write I square upon R or V, I square R or V square upon R. So the instantaneous power term I have to write as the VI, which is Vm sin of omega t into I m sin of omega t minus pi by 2, which I can write as minus cos of omega t. So I put that minus sign over here, I get Vm Im sin of omega t cos of omega t. And this, as you know that sin of 2 omega t is equal to 2 sin of omega t cos of omega t. Okay, sin of 2 theta is equal to 2 sin theta cos theta. So I get this relation written like this. So Vm into Im upon 2 sin of 2 omega t, or I can write, because V root 2 is equal to Vm and I root 2 is equal to Im, so I can write it simply as minus Vi sin of 2 omega t. Okay, so there is no problem in that. But let us take the power average over a single cycle. So this power average will become the power average of this quantity. Vi is, I can take it out, and this will be equal to 0, because the average of sin of 2 omega t over a cycle is taken as equal to 0. And this I can do mathematically like this, that 0 to t sin of 2 omega t dt is equal to 1 upon 2 omega minus cos 2 omega t, 0 to t, and when I put the values over here, this becomes equal to minus 1 upon 2 omega cos of 4 pi minus cos of 0, and cos of 4 pi is equal to 1, cos of 0 is also equal to 1, 1 minus 1 is equal to 0, so the whole thing turns out to be equal to 0, and therefore there is how much power we spent per cycle. In the case of inductor, that power is equal to 0. Okay. Of course, there is power which is stored at any instant of time when the current through the inductor is equal to I. That power is, that energy is, energy is equal to half Li square. But there is no power which is there, just like in the case of the Raja beta resistor, where the power was equal to Vi like this. Okay. So now next we apply the AC to another very important element, and that is our friend capacitor. Okay. Q is equal to CV. Okay. Next we take up the sister of the inductor. Okay. That is capacitor, for which the famous formula is Q is equal to CV. Okay. So we can write V is equal to Q upon C, or Vm sin of omega t that we apply over here is equal to Q upon C. But I, the current which is there, is defined as dq dt. So what I do is, we differentiate this. So d dt of Vm sine of omega t, dv dt is equal to omega Vm sine of, by my method, omega t plus pi by 2. Okay? Which will turn out to be equal to omega Vm into cos of omega t. So this is equal to 1 upon c, and dq upon dt is equal to I. So I am just writing it quickly as equal to this. So from this relation I can say that I is equal to omega c Vm sine of omega t plus pi by 2. Okay, r cos of omega t. So this I can write as I is equal to Im sine of omega t plus pi by 2, where Im is equal to, I can say from here by comparison, omega c into Vm. Okay. Or I can say that Vm is equal to 1 upon omega c into Im, which I write as xc into Im, where xc becomes equal to how much? Vm upon Im, using the nuances of Ohm's law. So Vm upon Im is equal to V root 2 upon I root 2 is equal to V upon I is equal to 1 upon omega c, and this is the capacitive reactance. Okay. So friends, I just plot this capacitive reactance as a function of omega, and I find a curve like this, which decreases as the omega is increased. So the capacitive reactance decreases with the rise in the value of omega, and we found that in the case of inductive reactance it was rising with the, that means the faster the change, the more the XL, and the faster the change, the less the XC. Now let's take from what we have done in the last one, that the instantaneous value of power P is equal to VI. There is no resistance, so no Raja beta concept. So I write this V as Vm sine of omega t, I as Im cos of omega t. So I get this as equal to Vm Im into sine of 2 omega t divided by 2, because I told you that sine of 2 omega t is equal to 2 sine of omega t cos of omega t. So I can write this as equal to Vi sine of 2 omega t, because Vi becomes equal to Vm Im upon 2, right? And then we take the average power per cycle. When we try to find out this average power per cycle, we find that this is equal to Vi into the average value of sine of 2 omega t over a cycle, which I have proved in the last one is equal to 0 always. Okay, that is cos of 4 pi minus cos of 0, 1 minus 1, and that will turn out to be equal to 0. To find out the average, we have to divide it by the time period, etc. But anyway, this will be equal to 0. So our two friends, the inductor and the capacitor, which gave XL and XC, they do not consume any power, but they do have, in this case, half CV square, in the case of L, half Li square. They are the energies which are stored in these devices. So these are energy storage devices, as opposed to the Raja beta R, which is energy dissipating devices, dissipates energy according to Joule Coulomb. So that is it for the day. Next we come with Ncr circuits, also known as RLC circuits, the series circuit. And as I told you the other day also, if I don't have an L, I have only, I put the value of L 0, then CR circuit, RC circuits, and if I take the value of C as 0, then LR circuits. Will talk in one go about the RLC series circuit, etc., and we'll also discuss what is known as the condition of resonance in that case. I wish that when you come back, please come prepared after reading that, and we'll see that the life is easy with the help of, oh, I didn't tell you here that there is the phasor V and here is the phasor I. So if I have it like this, then always this phasor is leading this one, which is evident from here also that, look here, this position and this position. Compare this position and this position. So all the time we find that the green curve is leading the red one, or the red one is lagging behind the green one, with the same kind of logic which we applied to the case of inductance. So we always know that by my method I can immediately compare the phases. The phase of I is ahead of the phase of V by 90 degrees or pi by 2 radians. It's otherwise in the case of inductor, and we'll see how the application will be there. If I take off the R, then there is LC circuits, and the LC circuits give us the oscillations. Okay, and we'll talk about the oscillations also in the due course of time. Thank you very much.